Now I'm going to introduce the A-star algorithm. This algorithm is used commonly in practical applications. It's pretty fast, but we can't analyze its time complexity in general because its speed depends on how good a heuristic is used, and I'll get to what a heuristic is in a minute. We start with a weighted graph. Here I've shown you a directed graph. We could have an undirected graph, which is a directed graph with directions in both directions, arrows in both directions. So here our idea is to try to find the shortest path from S to T. So here's S and here's T. Now, you can see, eyeball it very clearly, that the shortest path goes through A, but of course we're not supposed to do that. We're supposed to look at an algorithm here. All right, now the algorithm is based on a function which we call the heuristic, and the heuristic has to be given as part of the input. So this is actually the input of the problem. The directed graph with weights, the weighted graph, which may or may not be directed, and a heuristic value for each vertex. Now, it can't be any old function. We'll say that the heuristic value is admissible if the value, which we call h of x, is less than or equal to the actual minimum cost from that node x, shall we say, to t. Now we don't necessarily know what these values are for all t, but we have to be certain that this is true. If it's not admissible, then we might not get convergence. Now it's also desirable that h be consistent. This looks a lot like the triangle inequality. Basically, the value of the heuristic at any given point is less than or equal to the distance to another point plus the heuristic at that point. Now, one fact is that if h of t is 0 and if the heuristic is consistent, then it's automatically admissible. All right, now we're going to compute the cost. Now this value, I'll call it g, is the true cost of the shortest path from x to x when we're done. And we're going to compute that in some kind of order. Now what happens here is we're going to use a structure, a min-heap structure, to hold what's called the fringe, which are all the partially processed nodes. Initially, only one node is partially processed, and that is the start node, whose blue value, or g value, is 0 initially. Now, every node where we compute the cost, which is what we call g, we then can compute the estimate, which is defined to be f, which is g plus h. G of x plus h of f of x. So in this case, the estimate at s is 10. The red number is the sum of the blue number and the green number here, using my colors. Now, the nodes which we have visited but not fully processed are held in a structure min-heap, and when we delete them, we delete the node that has the minimum value of the estimate, which is f, g plus h. So when we delete a node from this, the first node we'll delete is the only one there, which is s. And once we delete a node, we then insert all its out neighbors that are not already in the structure. So in this case, we're going to insert B and A, and those red lines are the back pointers. And let me briefly say that we have a value of 4 and a value of 5 for the actual cost, g of x here. And here we get a value of 7 and a value of 9 for the estimate by adding the blue and green numbers there. So now at this point, S is no longer here, but A and B are here. And the one we delete is the one with the smallest value of the estimate, which is B. So B is deleted, and its out neighbors are then inserted into the... we have to do this one now. How come I neglected that? This has a blue value of 8 and a red value of 28. All right, now we delete B, the smallest, has the smallest red value, and we now push its out neighbors. Now the out neighbors of B, there's only one of them, which is T, and so we get an actual cost value of 11, which gives me a heuristic value, or I should say an estimate value of 18. No, of 11. All right, now, we're not done because we still have an object in the bin heap. And what is that? That's A, and we're going to push the value there. We're going to see what happens. Well, what happens is that we get a new improved value of the cost, which is 9, and this gives us a new lower estimate, which is now also 9. And we delete this back pointer and we substitute this back pointer. Now at this point, we can be certain that we're not going to go any farther. And this is the reason for that is that the value here of 28 is too big. So we can stop, and we have computed the minimum path from S to T, which is SAT. And you notice that we never even looked at D. The time savings of the A-star algorithm are derived from the fact that we